Today we are going to learn Chapter 1, Basic Electric and Magnetic Circuits. Chapter 1 has 8 sections. 1.1 is Introduction to Electric Circuits. Section 1.2 is definitions of key electrical quantities. Section 1.3 Idealized voltage and current sources. Section 1.4 Resistance. Section 1.5 Capacitance. Section 1.6 Magnetic circuit. Section 1.7 Inductance. And Section 1.8 Transformers. Most of Chapter 1's contents were taught in Chinese when you were in middle school and high school. Now we need to learn this again in English. The key to learn Chapter 1 is to master the technical terms. Therefore, I put the technical terms of Section 1 in this slide. You must read Section 1.1 and master these technical terms because these technical terms are the basics of the courses. Now let's learn Section 1.2, Definition of Key Electrical Quantities. An atom consists of a positively charged nucleus surrounded by a swarm of negatively charged electrons. The charge associated with one electron has been found to be 1.602 multiplied 10⁻⁹ coulombs. 1 coulomb can be defined as the charge on 6.242 multiplied 10⁻18 electrons. Section 1.2.2 is the concept of current. In a wire, when 1 coulomb's worth of charge pass a given spot in 1 second, the current is defined to be 1 ampere. The current is equal to dq divided by dt. Negative charge moving in one direction consists of a positive current flow in the opposite direction. In other words, the direction of current is opposite to negative charge moving direction. When charge flows at a steady state in one direction only, the current is direct current. We use symbol DC to represent direct current. When charges flow back and forth sinusoidally, it is alternating current. We use symbol AC representing alternating current. Section 1.2.3 introduces Kirchhoff's current law. Kirchhoff's current law says, at every instant of time, the sum of current flowing into any node of a circuit must equal the sum of the current leaving the node. Graph A shows the sum of the current into a node equals to 0. Graph B shows that, that the sum of the current leaving the node is 0. Graph C shows the sum of the current entering a node equals the sum of the current leaving the node. Section 1.2.4 shows the concept of voltage. Voltage is defined to be the amount of energy given to a unit of charge. Therefore, voltage is defined as dW divided by dQ. While currents are measured through a circuit component, voltage are measured across a component. Therefore, the voltage drop from point A to point B is described using VAB, where VAB is equal to the voltage at point A minus the voltage at point B. Therefore, VAB is equal to voltage VA minus VB. Section 1.25 introduces Kirchhoff's voltage law. Kirchhoff's voltage law says the sum of the voltages around any loop of a circuit at any instant is zero. We can see from the graph to describe voltage, a reference point in a circuit is usually designated with a ground symbol. The ground symbol. Moving the reference node around changes the voltage at each node, but doesn't change the voltage drop across the component. This means that although the reference point has moved, the voltage at each point could be different. However, the voltage drop across the resistance R1 is always the same, equal to 3 volts. Section 1.26 and 1.2.7 introduce the concept of power and energy respectively. Power and energy are two terms that are often misused. Energy can be thought of as the ability to do work, and it has a unit such as joules or BTU. Power is the rate at which energy is generated or used, and therefore it has a rate unit such as joules per second or BTU per hour. Therefore, power is defined as dW divided by dt. It can be rewritten as dW divided by dQ multiply dQ divided by dt. Since dW divided dQ is voltage and dQ divided dt is current, therefore dW divided dt is equal to voltage multiply current. So power is equal to voltage multiply current. Since power is the rate at which work is being done, therefore energy is the total amount of work done. Energy is equal to the integral of the power. Energy can be expressed in terms of joules, where 1 volt-second is equal to 1 joule. In electric power industry, the units of electrical energy are more often given in watt-hours. For large quantities, kilowatt hours or megawatt hours are used. For example, in your home, we usually pay electricity in terms of 1 kilowatt hours. For the power generation plant, we usually use megawatt hours to measure the energy produced by the power plants. Section 1.2.8 summarizes the key electrical quantities and relationships. Charge is represented using symbol Q. Charge's unit is a coulomb. The abbreviation of charge is C. The charge is defined as integral of current. Current is represented using symbol I. Current unit is ampere. The abbreviation of current is A. The current is defined as dq divided dt. Voltage is represented using symbol V. Voltage unit is volt. The abbreviation of voltage is V. Is capital V. The voltage is defined as dW divided by dq. Power is represented using symbol P. Power's unit is joule per second or volt. The abbreviation of power is W or joule G divided by S. The power is equal to dW divided by dt. Energy is represented using symbol W. Means work being done. The unit of energy is joule or watt-hour. The abbreviation of energy is using capital J or capital W multiply H. The energy is defined as integral of power.